Okay, for physics, your best bet in preparing for the physics part of your final exam is to not be looking at pictures on your phone while I'm talking, and to be practicing problem solving. Right? You've got the worksheet booklet from the physics unit, okay, that's got lots of problems in it with the answers, okay? You've got your quizzes that are worth going over. So if you go into Power School, okay, click on a quiz. Remember, there's going to be 2 links in each quiz. So if you open up the quiz, there'll be a link that says, quiz 2 questions, and then there'll be podcast of quiz 2. Okay, try the questions and then play the podcast, see if you did it right. Okay, that's a great way to study for both chemistry and physics. Okay, is to kind of watch the problems get solved again in case you don't get them right. But the big thing is practice, practice. It's such a skill-based unit. Okay, so we really need to make sure we know how to do all of that stuff. Okay, there's not nearly as much stuff in the multiple choice for physics other than like types of energy and things like that, the recall kind of stuff that we went over like the first couple of days, laws of thermodynamics and things like that. That's the recall stuff. That's really it. The rest of it is all, do you understand work energy theorem? Can you do an acceleration problem? Can you analyze a graph? Can you do this kind of stuff? So there's lots of analysis, mathematical analysis and problem solving for physics. Okay, much more so than any other. All right, everybody with me there? Okay. All right, so first day of the physics unit, we went over the different types of energy. That's going to be multiple choice only. All right, so, wind blowing over the prairie would be an example of what kind of energy, and the answers might be chemical, solar, potential, mechanical. Okay, mechanical would probably be our best answer there. Okay, because it's probably just kinetic, but kinetic is part of mechanical, so mechanical would be the best answer. Okay, so make sure you just kind of go over that and be able to recognize them. Really, you just need to read and recognize. See, general recognition, that's what you need to have for the types of energy. Okay, and then thermodynamics. Okay, we went over the 2 laws of thermodynamics. The first law of thermodynamics is just the law of conservation of energy. Energy can't be created or destroyed. You can transfer heat, okay, to something. You can do work on something that can change its energy, okay, but energy is always conserved. Okay, there could be some multiple choice questions that are a little more application based about the laws of thermodynamics, right? But there's not going to be much written response stuff, okay, about the laws of thermodynamics. Okay, so remember that the second law is about heat flow, that heat always flows from hot to cold, energy always goes from high to low. Okay, that's important because a lot of our technology relies on that. Okay, examples of things that use the second law, we talked about heat engines. Okay, example of something that goes against the second law would be heat pumps, like your refrigerator or an air conditioner. Okay, they take the heat from the hot area, they use energy and pump it out into the colder area, or sorry, into the hotter area. Okay, so they go against, it's like active transport, but for energy. Okay, so those are all examples that could pop up in a multiple choice question, and you would need to recognize which law of thermodynamics do they go with. Okay, and then we talked about scalar and vector quantities. Okay, the important part of scalar and vector quantities is that if I give you a question in the written response, it says, you have an object that starts from rest and accelerates at 22 meters per second squared to the right for 5 seconds. What's the final velocity? You need to remember that you're solving for velocity, which is a vector quantity, and thus your answer needs a vector. Okay, that's what you need to know scalars and vectors for. Okay, you also need to know it a little bit for graphical analysis because sometimes something goes into the negatives, and so we have to make sure that we keep in mind negatives and positives when we're doing the math. Okay, really that's what you need to remember. So remember what things are scalar and what things are vector. Okay, because that'll be important for your exam. So if we're looking at vector, scalar versus vector, okay, we got v equals d over t. The v with the arrow over top is velocity. The d with the arrow over top is displacement, okay? And then we got speed is distance over time. So just remember that, we solve for those a little bit differently, okay, if we're looking at a question. Okay, one of them direction matters, one of them it doesn't, okay? So things like that. Also remember that displacement is final position minus initial position. You don't have to memorize that. It's on your formula sheets, on your data sheet, okay? But it's a formula that we forget about, even though it's on there. We forget that we can solve for displacement by taking the final position and subtracting the initial position on a graph is where most people forget about that. Okay, so make sure you remember that so that you can use it when that comes up. Okay, so will there be V equals D over T problem solving on the final? Yes. Will it be in the written response? No. Okay, I'm not going to waste a 5-mark problem on a final exam for V equals D over T. Okay, that's not going to challenge you at all. So if there's a V equals D over T calculation, it'll be a multiple choice question. Okay, it's a simple calculation. All right, acceleration. Okay, we talked about acceleration after that. Okay, acceleration is the change in velocity over time. Okay, expect a written response problem to do with acceleration. Okay, I think you had 2 on your unit exam. Okay, you had 2 acceleration problems on your unit exam. Okay, one of them was somebody threw something off the top of a building straight downwards, okay, or something like that, and you had to solve for the speed it would hit the ground at or something. Okay, so definitely make sure you're familiar with how to manipulate and use the acceleration formula. Okay, how important is graphing? Okay, very important. How many marks on your unit exam were to do with graphing? I'm actually not looking for a number. Was it a lot? Yes, it was. Graphing is important, okay? It is one of the most crucial skills in any science. Being able to visually represent your data using a graph is crucial. So being able to interpret and analyze a graph is also crucial. So expect graphs in the multiple choice, okay? The graphs in the multiple choice will be interpretation. All right, so I show you a graph and I ask, based on the shape of this position versus time graph, what type of motion is going on? A, constant velocity, B, stopped, C, acceleration, D, can't tell, whatever. Okay, be something like that. So expect that there'll be a few graphs in the multiple choice where you'll have to do some basic interpretation of what's going on. Okay, there will also be some interpretation and analysis of graphs in the written response. Okay, so if, for example, I gave you a graph that looked like this. Okay, a position versus time graph, and I said, describe the motion in each lettered part of the graph. Okay, what I'd be looking for here is something like this. Okay, in part A, what's the object doing? Moving forward at a constant velocity. Perfect. Okay, you've identified that it was a constant velocity. You've identified it was forwards or in a positive direction. Those are the 2 things I'd be looking for. Okay, in part B, the object is stopped because this position is unchanged. Okay, in part C, moving backwards at a constant velocity. Part D, stopped. Okay, that's what I'd be looking for if I was asking you to interpret. Right, you don't want to just say moving at a constant speed. That's not as good as moving at a constant velocity forwards. Okay, one is way more descriptive than the other. I'm not saying that moving at a constant speed isn't right, but it's not worth full marks either. Okay, this is a position versus time graph. It's dealing with vector quantities. Okay, you need to include that kind of detail. Everyone follow? Okay. All right, so be able to read them, be able to interpret, okay, be able to extrapolate. Y equals mx plus b. We generally did pretty good on the y equals mx plus b part of the unit exam. Okay, we had the position versus time graph, and I asked you to make sure you can, calculate what the position would be after 10 seconds, okay, or what the how long would it take to reach this position, and you guys were fine with manipulating y equals mx plus b. Okay, but expect that I'm probably going to ask you to do that again on a written response item. Okay, I may also ask, we're using different kinds of graphs, okay, that you identify what the slope represents. Okay, something like that. Or, here's a velocity versus time graph, calculate the displacement. Okay, anyone remember how we calculate displacement on a velocity time graph? Right, we find the area underneath the line because that is essentially taking average velocity and multiplying by time, okay, like this. Okay, it's just a manipulation of v equals d over t. All right? So important that we can show that we still know that. Okay, remember that anytime you see the words using your graph, that you should be using your graph. Okay, y equals mx plus b, not some other formula. Okay, if it specifically says using your graph and its equation, make sure that's what you do, because a few people didn't do that on the unit exam on that question and lost marks as a result. Okay, so make sure that if it says using your graph, that you're using stuff only on the graph, nothing else. Okay. All right, so for position versus time graphs, okay, remember that our slope equals velocity, okay, so that would be y minus b over x equals m, okay, that would equal velocity on a position versus time graph, because when we do that, it's essentially final position minus initial position, right, because it's y is position and x is time, okay, so that's how it works out. If we have something like this, like a position versus time graph that's kind of zigzaggy like this, and I want to calculate the total displacement, how would I do it? Final minus initial. Here's my final position. Here's my initial position. I just subtract them, right? This is a position versus time graph, so that's all I have to do. Okay, but if I wanted to calculate the total distance traveled, would that work? No. Okay, if I want to calculate the total distance traveled, I need to know how far did I go here? 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 And add them all together, because it doesn't care about direction, right? Displacement is how far from your starting position and in what direction are you? Distance is how far did you have to go to get there? Okay, they're different things, so make sure we remember that. Okay, so that's for position versus time. Okay, and then we just talked about this displacement is final position minus initial position. Distance, add all the sections. Okay, so we just talked about that. And then we got velocity versus time graphs. All right, when we calculate the slope of a velocity versus time graph, okay, we're still going m equals y minus b over x, but now it's final velocity minus initial velocity instead of position divided by time, which is acceleration. So the slope of the velocity versus time graph's line is acceleration. So there could be y equals mx plus b with a velocity versus time graph, or there could be a graph, a velocity versus time graph that looks like this one, okay, that would ask you, what's the acceleration in part B? What's the acceleration in part B? 0. It's traveling at a constant velocity according to that graph. Okay, if I wanted to calculate the displacement, okay, then I would have, okay, those shapes that I would have to calculate. This rectangle here, this triangle, and this rectangle. Okay, average velocity times time gets me the area of those shapes, and then I would add them together. Okay, things like that. So definitely expect that I'm going to ask you to do exactly the same things I asked you to do in the analysis of your 2 labs. Right? We did the position versus time graph lab at the carts out in the atrium, and we did the acceleration lab, okay, the need for speed lab, okay, with the acceleration data. Expect that what I asked you to do in the analysis of those 2 labs is what I'm going to ask you to do on the final exam. All right, so not a bad idea to look over those lab reports. Okay, yeah, and so we were just talking about this before. Okay, so for calculating displacement from a velocity versus time graph, we're taking average velocity multiplying by time. Okay, we're calculating the area of all the shapes when we do that, okay, and adding them all up to get displacement. All right, so keep that in mind. That's for velocity versus time graphs. Okay, after graphing, we talked about work energy theorem. Okay, and work energy theorem has to do with when you change the mechanical energy of an object or system. Okay, in order to change the mechanical energy of an object or system, you have to do work. Okay, so you do work, that changes the energy. Or the object or system does work on something else and it loses the energy because it's giving it to something else. Okay, the examples that we looked at, were like a bow and arrow. Okay, you draw back a bow using X amount of force over a certain distance. What speed will the arrow leave the bow at? Okay, well, when I let go of the bow, all the work I did becomes kinetic energy in the arrow. If I aim the arrow straight up in the air and I let it go, okay, then eventually all the work I did will become potential energy, okay, and so on. So expect that you'll get questions exactly like what we did on the quizzes on work energy theorem and exactly like what were on your worksheets. I'm not going to do anything different. Okay. You'll probably have a work energy theorem question about work and potential energy and a work energy theorem about work and kinetic energy. Okay? Exactly like what we've done in class. Okay? I'm not going to change anything or make it more difficult, okay, at this point. It's going to be exactly like what we've done before. Okay, so for work energy theorem then, okay, there'll be some understanding in the multiple choice, so a few questions just about what work energy theorem is and how transfer of energy can change things, okay, but mostly it's going to be this. Work is force times distance, which causes a change in mechanical energy, okay, so that'll be final minus initial, okay, so it could be potential or it could be kinetic, right, either one, or there could be one of each. There was on your unit exam after all. Okay? But again, we did pretty good on those, okay, on the unit exam, but it's still worth reviewing so that we get those marks a second time. Okay, and then we talked about the law of conservation of mechanical energy. All right, so we talked about, kids sledding down a hill, a roller coaster, a person jumps out of a plane, whatever. Okay, any situation where there's no energy being gained or lost. Okay, a roller coaster in the perfect physical world gains or loses no energy at all. The energy at the top of the first hill is the same as the energy at the end. Okay, so we can calculate, how fast it's going at the end or how tall was the first hill based on the other information that we have. Okay, so there will definitely be a roller coaster question. Sorry, I mean law of conservation of energy. Sorry, I slipped up there. There's a roller coaster question on your final. Okay, make sure you know how to do those ones. Okay, just EI equals EF. Okay, and okay, that kind of thing. Remember that mechanical energy is potential plus kinetic. Okay, and then there's an example here. Okay, if we had for example, a 20 kilogram object. You know what? Let's see how many of you can do that. Why don't you try that one right now? Okay. I got a 20 kilogram block sliding down a hill. Okay. It starts at 4 meters per second, 20 meters above the bottom of the hill. A little while later, it's moving at 10 meters per second. I want to know how high above the bottom of the hill is it at this point. Okay. Let's see how many of you remember how to do that. Give you a couple minutes. So it's a law of conservation of energy question. So we know right off the bat that the initial energy equals the final energy and that it has both kinds of energy at both places. It has potential and kinetic in both locations. So that's going to mean m times g times h initial plus 1/2 mv initial squared equals m times g times h final plus 1/2 mv final squared. Okay, we can take the mass out. Mass is in every term, so we can cancel it. If you're not comfortable with that, you can leave it in and just use 20 kilograms. You'll get the same answer. Okay, I'm looking for the final height. So I'm looking for HF. So I'm going to bring the 1/2 VF squared over to this side by subtracting it first. So that'll be GHI plus 1/2 VI squared minus 1/2 VF squared. Okay, and that's going to equal G times HF. Now I just divide both sides by G. Okay, and I've got HF, so I just plug in my numbers. So that'll be 9.81 times 20 plus 1/2 times 4 squared minus 9.81 times, sorry, not 9.81, minus 1/2 times 10 squared, okay, divided by 9.81. Okay, so when we do that, I think I have the answer down here. 15.7 meters. Okay, is what we're going to get for that one. Okay. Okay, questions on how that one worked? Ringing a bell? All right, and then the last thing we talked about was efficiency. Okay, and efficiency is, I think there's one efficiency question in the multiple choice. Right? Don't spend a lot of time on it. Just know what efficiency is. Okay, efficiency is how well is the input energy turned into effective work. Okay, that's what we're looking for there. All right, so that'll be multiple choice only. Okay, so that's what's going to be on there in terms of biology and physics. Okay, all right, questions from you guys? Got things you want me to cover in a bit more detail or show you? Okay, besides what I've shown you, what do you want to see? Like a what? Okay, I showed you a couple already. I don't know how much more I can show you that's going to be any different. Okay. Okay, so if I got a velocity versus time graph that looks like this, okay, it's just linear. You know, I might ask you, how fast will the object be going after 20 seconds? Okay, so since this is a velocity versus time graph, what does the slope represent? Acceleration. Okay, I'm asking you how fast something will be going after 20 seconds. Am I looking for y or x? X is in seconds, y is in meters per second. Am I looking for y or x? Y. Okay, I'm asking you how fast something's going to be going. You're looking for a y value. I told you after 20 seconds, that's an x value. Okay, so all we would do is go y equals 0.572 times 20 seconds plus 2.5, and we would have the speed it would be going after 20 seconds. Okay, I could have also said, how long will it take the object to reach a speed of 100 meters per second? Okay, in that case, I gave you a y value, and I'm asking for x. So I would manipulate, okay, x will be y minus b divided by m. So that'll be 100, the value I gave you, minus 2.5 divided by 0.572, okay? And we'd be able to calculate how long that would take, okay? So just manipulation of the graphing equation. Other thing to do with velocity versus time graphs, okay? I could ask you for the displacement over the whole trip. Okay, so if I asked you for the displacement over the whole trip, okay, then we'd be looking to calculate some shapes here. So I would have this square, this big rectangle, this triangle here, and that triangle there. All right, so I would go for this rectangle, it'll be 6, 3 times 2. Okay, for this triangle here, it has a height of 2, okay, and a width of 2. So it's 2 times 2 divided by 2, so its area is 2. Okay, this one is going to be 5 meters per second high by 4 seconds long. All right, so it's going to have 20 meters. Okay, this one is 2 seconds on the base, 5 seconds high. 5 times 2 is 10, divided by 2 is 5. Okay, and then this one here is 4 high by 2 wide. 4 times 2 is 8, over 2 is 4, but it's negative. Okay, so then I add them together. I got 28, okay, 33, 31. Okay, total displacement 31 meters. If I asked for total distance, it would be 35 meters. Okay, something like that. All right, for your position versus time graphs, the only thing I could ask you to do is calculate velocity. That'll be v equals d over t, okay, or displacement, final position minus initial position. There's really not much else to ask you to do with the graphing. So as intimidated as we were by graphing, there's really not a lot of things I can ask you to calculate based on what we've done with the graphs. Okay. All right, what else? I'm getting this Coder, we're so tired of reviewing, will you just leave us alone vibe. Don't get tired of reviewing, you have a lot more of it to do. Okay. Sorry, reality check there. Smack. Okay. Okay, well, you got your review package. There's lots of physics in there. Okay. Maybe start having a look at some of those and see if any of those are giving you trouble or going to trip you up, and we can go over them if there's questions. Okay, but let's make sure we're using our time to do a review here. Remember, tomorrow is a unit exam day. Okay, so make sure that you're prepared for stuff on climate and energy transfers and wind patterns and specific heat capacity and latent heat and biomes and climatograms. Okay, for tomorrow. So we got evaporation, transpiration, which is kind of one step, right? Because they happen together sometimes. Then we have condensation, precipitation, runoff, infiltration. 6. When it goes into the ground. Yeah. Okay. All right. Hopefully some more questions will come up. So please ask. Okay. Happy to go over anything that comes up that you want to work on.